quiz number 3 here. We had 4 questions. Number 1, why are metals good conductors of electricity as well as heat? It's the same answer for both. And the answers, let's just go with this person said, they're able to move freely. That's correct. Good answer. The electrons are able to move freely in a metal. In a conductor, the electrons can move freely. In an insulator, they're kind of fixed in position, so you can't have motion of charge, which is conduction. Okay, I am going for a walk on a sunny and warm day. What's the best color shirt I can wear so that I absorb the least radiation and stay the coolest? What colors can absorb the least? White. What color would absorb the most? Black. Right? Black is the perfect absorber and emitter of radiation. White is a very poor absorber emitter. So if you look out the window, you see that we have snow everywhere. That snow, what color is it? White. What does that tell you it's going to do to the radiation? It's going to reflect a lot. So when you have snow, the ground reflects a lot more radiation, absorbs less, and so it contributes to staying colder because you're not absorbing as much of the radiation from the sun. Molecules in solids can't move from their relatively stationary positions, but their centers of charge can move. This distortion of charge in the atom or molecule is called obviously it's a kind of polarization, and it's electric polarization. Okay, final question. In the demonstration class, when you put, okay, so the student wrote this, so that's why they said when you, and I didn't catch that in the editing. Put the ball on a stick above a fire. Hopefully you all recognize that description. What happens to the ball when heated? It expands temporarily. When is it going to contract? It's going to contract when it cools back down. Okay, so there were our answers. A, B, D, A. ABDA, as we would never say. And let's get to the lecture. Before I actually jump into the lecture, though, I want to talk about scheduling. Just before class, one student asked, is the test on Wednesday? No, Wednesday is scheduled for a review lecture. And then the test is scheduled on Friday. But oh great. There's mold growing on this plate. And there's rust growing on this mass. That's my fault. Now there's water growing on this plate. I have a request to make, and my request is to postpone the exam by a week, which means we'll start in on chemistry on Friday and have the exam the following Friday. And I'll give you the reason. My grandmother died on Friday morning, and the funeral is, because of scheduling issues, it won't be until Friday the 23rd. And so I'm going to fly out to California. I'll not be here for your lab, but that'll be okay because Alex can take care of your lab. But I won't be here for class Friday. And so my plan is to give you the exam while I'm gone. That way we don't miss any lectures. Okay, so you would ask a question?
Yeah, so then it's not going to be this Friday. It'll be next Friday?
Right, it'll be postponed 1 week.
Okay, awesome.
So this, I was actually going to make it a clicker question so you could express if you are against this, because moving the exam is kind of a dicey thing. If anyone is opposed, hopefully you don't feel bad about saying it. Is anyone opposed to moving the exam back a week? Okay, so it's going to be on the same material. Our lectures will then move forward. One other thing, do you prefer to have a review lecture closer to the exam or on the schedule on Wednesday and then have it a week and 2 days after the review lecture is the exam?
I don't know. Everyone could sleep.
And what?
I just say, I don't know, for me, I would say still do it on Wednesday so we can have the reviews and then all the time to prep.
Yeah, that was what my question was. What should you prefer? Danny? Okay, yes, that's a good point. The review is definitely not, this is what's going to be on the test. The review is, this is what we've covered. And so what's on the test can be from this broad range. So the review is not specific, learn to answer this specific question, learn to answer this specific question. It's going to be, we have this broad range.
Yeah, I think Wednesday would be better. That way we have an idea of what we should really be studying.
Okay, so I'll stick with the lecture schedule for Wednesday's review, and then Friday we'll start chemistry. We'll continue chemistry on Monday and Wednesday, then you'll have the exam on Friday.
So then it will only, just two questions, will it only be on physics section?
Yes,
Oh,
that's
no matter
going to be on
what? Okay.
physics stuff.
And then, again, I wasn't here for the first day, do you have drop exams? Do you do
No.
that? Okay, so it's all the exams, okay, awesome.
Now, one more thing that just came into, and sadly I think went out of my mind. What was it? Wow. There was another important thing about this I had to say, and I can't remember what it was. It will probably come to me mid-sentence, and I'll just blurt it out because that's the way I roll. Oh, yeah. There's no homework this week. That was the thing. There's no homework this week because we didn't have school on Friday. And initially my plan was, of course, to have the exam this coming Friday. And I didn't want people to be, I don't have time to stay for the exam because I'm doing the homework. And it's kind of too late to assign homework now that we put off the exam by a week. So, we're not going to have the punitive, ha ha ha, you selected this. But there will be a homework assignment that I will probably post, by Wednesday for next Wednesday. So you'll have it a little earlier than normal. And it will be covering the end of the physics topics as well as probably a little bit of chemistry. And as you might guess, the topics are closely related. So it's not like the little bit of chemistry that would be on there would be unbeneficial. It's going to be starting with electrical things. You had a question.
How do we access this? Is this on your YouTube?
Well, you can watch them on the YouTube, or you can go to the OneNote where you have all of these slides.
Okay, do we have to log in anything?
OneNote, you need to log in with your Union College OneNote account. So if you have already downloaded the free Microsoft Office from Microsoft, of course, that's the account that you need to log in with OneNote.
Okay. And then the questions on the exam, they're going to be some of the ones we wrote and some of the ones that you want.
Right. It'll be half questions that you wrote and half questions that came from the textbook.
Okay.
That when I say from the textbook, they're not ones that are in the textbook. They're ones that the textbook includes as test questions to go with it. Right. Well, just to make sure you don't think it's coming from the homework questions in the textbook. It's coming from the test question bank that comes with the textbook.
Okay.
Right. Just, I don't want people, I couldn't find this question anywhere. They don't publish the questions that they put in the question test bank. Okay. So the last chapter in our physics section is talking about waves. And I actually want to start with a fun demonstration. Fun demonstration. If you think of a physics demonstration that's not fun, the answer is no, just in case anything is thinking about it. Incorrect, snarky answer. I will need someone to help me out. No one yet has taken the opportunity to get extra credit with this. So would somebody please volunteer? Come on up. Okay, I love the enthusiasm. Me. Okay, so your job is going to be here pretty simple. I just want you to hold this with your hand like this. So when I say there, you can just clamp down and have it so this doesn't slide. And me, I'm going to do the fun thing. I have a tuning fork. You bang a tuning fork, it plays a note. Interesting enough on its own right. If you put it on a surface, you can actually hear it louder. And of course, this being science class, the first thing you might say is, why do I hear a note, a specific note, not just some random buzz when I bang it? Right, that's something interesting that it makes a specific, really high pitch when I bang it. And the second thing is, when I test this, why would it be louder? Well, we're going to study sound waves, so we don't really have much scientific theory about that yet. But this thing here, I think you'll really, well, I love it. Okay. So I put this over the top of the tube, and I'm going to raise the tube. Okay, hold there. Much louder when I put it over the tube. And then I'm going to raise it some more, so let it go. There's another place where it's louder. There's another place where it's louder. So it has multiple lengths where it's louder, where it's amplified. And so, you know, scientific, that's all. Thanks. But wasn't that cool? Yes, it was cool. Come on. I can't believe you guys aren't offside. That was awesome. So scientific method, something you know you're going to have a question on the test. What's the first step of the scientific method? You observe something that's interesting, right? And I always emphasize the interesting part. Observation will be a fine answer. But I emphasize the interesting part because you're really not going to be a scientist if you're like, not interested in these things you're observing. Yes?
Oh, wait, so first step is make observations and ask a question? Or I thought it was ask, or then you have to observe this, okay.
Ask the question is not part of the one that I asked you to look.
Okay.
So the first step was to observe something interesting. So you see something, you're like, wow, that's crazy. Why did that happen? Right? That's something
And
interesting.
you can make a hypothesis.
And then step 2 is to make a hypothesis that has 3 specific aspects. Number 1, it needs to explain why the thing we observed occurred. So explain why it got louder with certain heights of that tube. Number 2, it needs to be based on scientific ideas, not random disconnected ideas, but things that are already based on the scientific process, because science builds on itself. And then number 3, that makes predictions different than what you observe that can be tested. And so we would look at this, and we're going to try to come up with an understanding of sound waves so that we can go through the rest of it, have the scientific background to make a hypothesis. So as we go through, I'll come back to this and we'll try to hypothesize, so why did that occur? So starting out, vibrations and waves. We have some interesting definitions. A vibration is a wiggle in time. What that means, a vibration or oscillation, something going back and forth, back and forth. So that's what the in time is. If you were just to sit there and look at something, if it goes back and forth in time, you say, that's a vibration or oscillation. An example I like to use is my attendance at College View Church. It's something that's oscillatory. I am not there Sunday or Monday. I decided I didn't have time, so I'm not there for choir on Tuesday, or Wednesday, or Thursday, or Friday. But I'm there every Sabbath. That's oscillatory behavior because it repeats in time. It's a vibration in time. It's going back and forth to church. A wave, on the other hand, is a vibration or wiggle that travels. So that's when it says in space, that means it travels. So they go from point A to point B. Now sound, when I have that tuning fork or when I stand up here speaking, I am doing something up here and you hear it there. So something had to travel from here to there. That's what a wave is doing. It's transporting energy, or sometimes we'll say transporting information. You have to transport energy to transport information through space. And how is it doing that? With a wiggle. So it has both the oscillations, the wiggles in time, as well as the motion in space. Now, when we talk about waves, we have some important words, some important vocabulary words. So this here is showing you have a spring with a ball on it. And you just take that spring. Okay, so close enough. Here's a spring that has some scissors on it. Same idea. So if I pull this down and let go, it's going up and down. We call that oscillation or vibration. Now that picture is taking this and saying, okay, let us look at the position of the scissors as time passes. So you see it's down low, up high, moving up and down. And so this graph has simply put time, actually, the picture has distance, which I would not have done for this picture. I really would have put time on this because it's not moving. So let me change a word here, because this picture is not depicting what I wanted it to depict, and say that we have time on this axis and we have position on this axis. Now, this picture does make some sense in what they're trying to illustrate. It's not like the picture is in error. It's just not what I wanted to illustrate. So if I have position on one axis and time on the other, we have two important words here. Notice I crossed out wavelength. That's an important word, but that has to do with a traveling wave. And I first wanted to isolate on vibrations. I took it. There were two similar pictures, and I deleted one. In retrospect, there was a difference, the time versus the position. So the time for it to repeat is an important parameter. When I talked about me going to church, what was the time for me to repeat going to church? It is weekly, right? Every 7 days. Well, we call that time the period. So the period is the time for something to repeat. So we have lots of periodic things. The period for the Earth to do one rotation on its axis. What do we call that?
Oh, wait, a day.
Yes, a day. You answered my second question. A day is the time to do one rotation on its axis. What's the time to do one orbit around the sun? A year. All right, so these are periodic things as well. Lots of things. We won't talk about that at this moment. So the period is the time for something to repeat. The amplitude and displacement are closely associated words. Displacement is the distance from equilibrium. Distance from equilibrium. What does equilibrium mean? What does equa mean? That means equal. And what does the librium part mean? Pretty sure I talked about this back when we learned about equilibrium. It's forces. So equilibrium means equal forces. That's where the thing would naturally rest. So with my spring system here, the equilibrium position is this green dashed position. That's where the mass would just be sitting if it wasn't vibrating, oscillating. Vibrating, oscillating, same thing. The displacement is how far it is from that equilibrium position, the place where it would naturally be at rest. And the amplitude, because amplitude is the word that's on the chart, is the maximum displacement. So in this picture, you see the amplitude there is shown as the maximum displacement right there. But you could have also put it here. because the displacement is the distance from equilibrium, and it's going equally up from equilibrium and down from equilibrium. So the displacement is going from plus the amplitude to minus the amplitude. Question?
I don't understand what you said before. You were talking about place and I don't know what, and it was confusing. Like, you know how you, like before, what you were mentioning before, after you said equilibrium, and you started explaining how this works, and I'm kind of still confused.
Okay, do you understand the word displacement?
Yes.
Okay, so amplitude is the maximum the displacement can be. So if I have this thing oscillating, and here's equilibrium, and it goes up until it's 5 centimeters above, and then down until it's 5 centimeters below, and up again, then the amplitude is the maximum displacement of 5 centimeters.
Okay.
And displacement is the amount it is at any time. So period is the time to repeat. Amplitude is how big the displacement is. Now that's for vibration. So what I put here is vibrations. Now I'm going to erase my marks and go to the marks that were on this originally. So I'm going to erase my word time, replace my period with wavelength, and now I have, instead of time, I have position on the horizontal axis. Remember, a wave is an oscillation that travels. So what was actually intended with this picture is for me to take my spring scissor system, to set it oscillating, but then to walk sideways, and you're taking a video, essentially, of the height of the scissors as I was walking. And so now, the oscillation was traveling in space, so we have a wave. Now, it's kind of a hokey wave example, but you now have a position where it was at the highest point, a position where it was at the lowest point, and so on. So as it was traveling, you have positions, and you again have a repeating cycle where it gets to its maximum amplitude and maximum amplitude again, and we call that the wavelength. Wave because it's traveling, the length part because it's the distance for it to repeat. So the wavelength is the distance to repeat. What was the period? Time to repeat. So the difference in wavelength and period is one is distance to repeat and one is time to repeat. I just realized I didn't start the thing for recording your clicker answers yet. It's okay. We're only a little over halfway through the lecture and on the second slide. What could go wrong? Possibly.
So period is the time to repeat, and wavelength is the distance to repeat.
Yes, that's right. So I think the next slide is, nope, it's not good. Well, this here just is repeating the same picture, so I'm not going to focus on that. And yes, here is our first clicker question. Give me a moment because I was slow in getting started on this. I just completely forgot to start it. Let's blame it on any excuse we can come up with. That's lame, right? You have plenty of time to get your clickers logged in, though. And now you can answer.
What's the question?
That question. Oh. Apparently the question got deleted. It's a really good question. Then what's the question? This here is the question. The distance between adjacent peaks and the direction of travel for a transverse wave is its.
So does that mean B is A?
No, just answer B, C, D, E. I'm so sorry about that. I'm afraid I did these last night. Yeah, I'm pretty impressive. Underline some important words. There was one. Okay.
Oh, what was the question again?
The distance between adjacent peaks and the direction of travel. Okay. So we had all 7 people said it's the wavelength. And that is correct. Yay! The wavelength is the distance for it to repeat. Now, this said adjacent peaks. It actually doesn't have to be adjacent peaks. I could have gone from here to here. That's where it crosses 0, not to the next place it crosses 0, but to the next place where it crosses 0 going the same direction. Right? It has to repeat. Crossing 0 is not repeating. Crossing 0 going the same direction is repeating. So I could have chosen other places. I could have chosen right here to right here, right? At this specific displacement and going up. As long as it's repeating, you have the wavelength. And the same designation would work if you're doing the period. It just has to be the repeating. It's easiest to go maximum to maximum or minimum to minimum, because then there's no confusion, because it only gets to maximum when it's changing direction. Only gets to minimum when it's changing direction. So those, it's really easy to identify. Okay. We describe vibrations and waves with specific words. A vibration is described by, the word I used was period. I've got to get a new tip for this, you guys. It was in your class where I dropped and damaged the tip, right? Yeah. That's why it's doing all the skipping. So period is the time for a wave to repeat. We have another word here, frequency. Frequency is equal to 1 divided by the period. It's a very simple relationship. Frequency is 1 divided by the period. Since period is the time to repeat, then frequency is 1 divided by the time to repeat, or number of repeats per time. So frequency is how many occurrences per time. So you could say, for instance, the frequency of my church attendance is 1 over 7 days. 1 attendance per 7 days, or 1 per week, or if you prefer, 52 per year, with a certain uncertainty there because it's not exactly 52 weeks in a year. So the frequency is just 1 divided by the period. And we have a special unit for frequency, the hertz, written right here. A hertz is defined as 1 occurrence per second. So the electrical frequency, the frequency of electricity coming out of the power plug sitting on top of your desks, because the people who built the room couldn't read the instructions that said to put them underneath the desks. What's the frequency of that electrical power? Do you know? Electrical power coming out right in front of you. Well, to your right. No? It's 60 hertz. That's 60 hertz. That means that it is a wave that reaches a wave or an oscillation that reaches its peak 60 times a second. So it does 60 cycles in a second. What's the period then? How do I calculate the period if I know that 60 hertz for the frequency? Go ahead, just say the math. I don't want you to actually have to try to calculate it. I didn't hear.
1 over 60.
1 over 60, that's right. Since the frequency is 60 hertz and frequency is 1 divided by period, then period must be 1 divided by frequency. So the period is 1/60th of a second. 1 over 60 hertz means 1 over 60 per second, or put the seconds on top. So that means that the electrical power here has 60 cycles in a second, or the time between cycles is 1/60th of a second. So vibrations, we use the frequency or the period to describe it. Waves are traveling, so you also have a speed. And with that speed comes then the distance it travels in a cycle. And so we have the wavelength. The distance it travels in a cycle. We had the frequency, which was the time per, 1 over the time per cycle. And it turns out we have a simple relationship between the speed, the wavelength, and the frequency. Speed is equal to the distance over time. We learned that a long time ago in this class. So the distance it travels in one cycle is called the wavelength. And the time for one cycle is called the period. So the speed of a wave is the wavelength divided by the period. But since frequency is 1 over period, I can also write that. There you can see the top left, frequency is 1 over period. So I can also write that as the wavelength times the frequency. Now, you know what we don't like to do at all in physics? We don't like to write out all of these words. Why? Because it takes time, and you know what? We don't have time. Right? As we all most famously have heard, ain't nobody got time for that. So what do we write instead of speed? What symbol do we use instead of speed? Actually, we use V. V, short for velocity, which of course without the arrow is speed. Remember, with the arrow on top, it's a vector. It has speed and direction. Without the arrow, it's just the speed. Wavelength, we use the Greek L. So that's our symbol for wavelength. The lambda is the name for it. It's the Greek letter L. Wavelength, lambda. Not Y. It looks like an upside down Y, sure. And then for the period, we use the symbol T. T for time. Capital T is the period. Lowercase t time, capital T, the time for one cycle, the period. And of course, the symbol for frequency, simple, F. So we can write this equation as speed is equal to wavelength divided by period is equal to wavelength multiplied by frequency. Now, if you're taking a higher level physics class, we don't use F for frequency. We use nu. I don't know why. Greek letter N. So this here is everything that I wrote out in words in pink and in green above. Much shorter, that's why we use the symbols. So you should develop that familiarity that lambda is the wavelength, T is the period, and of course V is the speed we've already studied. Okay, once again, the question is the one that was marked as A, and it's open for answering now. So if the frequency of a particular wave is 20 hertz, what is its period? Fully expect Gabby to get this one because she was the one who gave us the answer last time. Do you go as Gabby or do you?
Yeah, go ahead.
I thought so. I thought you wrote G-A-B-I, right? Is that how you spell it?
G-A-B-Y.
Oh, B-Y. Just don't want to call you something you're like, I hate that. I don't know. Never. Okay. Every single one of you answered the same thing. Luckily, you were all correct. We have had it happen where every answer is incorrect, but so far we're on a roll. No one's been wrong today. which means probably I'm just going way too slow. But the frequency is 1 over the period, or the period is 1 over the frequency. So since we were given a frequency, remember hertz is 1 over seconds. So 1 over 20, 1 over seconds, 1 over seconds is seconds. So that's 1 over 20 seconds. And that's the correct answer that you all got. Didn't need that explained. Okay, I've already talked about everything on that. Time for more fun. I took my actual my Slinky into my office, so we'll use this to indicate two kinds of waves. We've already seen the word transverse, but now we're going to get a practical application. So hold in this one, please. This is a spring which is useful for showing how waves work. Okay. There's no perfect place for me to go where everyone can see. And I think most people can see here. Before I was just basically in line with Dan, I don't know. Okay, so one kind of wave. If I take this and I lift it up and let go, I'm going to have a disturbance that travels. That's what we call a wave. It's kind of hard to see because it travels so fast, but when I let go, the upward pulse came down here, reflected and came back as a downward pulse. We call that a transverse wave because the displacement, what's displacement?
The period.
Not time or period. Displacement has to do with distance. The distance from the equilibrium point. So equilibrium is this roughly straight line that it's taking down when it's still. So I made a displacement that was vertical with a roughly horizontal here. Make this horizontal now, vertical displacement. When I let go, I have a disturbance that is, displacement is vertical, but the velocity is horizontal. We call that a transverse wave because the displacement is perpendicular to the velocity. That's transverse. I could have also gone like this and pulled the little springs toward me. Now it's displaced horizontally. I let go and the wave travels horizontally. And of course, nothing in life is perfect. But now we have a wave where we had the spring getting closer and farther. So each little loop was displaced either left or right as the wave traveled horizontally. So the displacement was parallel or anti-parallel. Anti-parallel just means the opposite direction. To the velocity. We call such a wave as that a longitudinal wave. So transverse is velocity is perpendicular to displacement. Longitudinal velocity is parallel to displacement. Now let's take these words and apply them to a sound wave. When I am speaking, fundamentally, how do I make sound? Okay? I am pushing air out of my lungs. If I'm not pushing air out of my lungs, nothing happens. My vocal cords are vibrating. They're just flaps of skin that are slapping open and closed. And so what happens is the air that I'm forcing out is momentarily stopped, and then it goes again. Stop, goes again. So coming out of my mouth are bursts of air. So what direction is the displacement of the air molecules coming out of my mouth? Very simply, when I have blow air out of my mouth, what direction are the molecules moving when they come out of my mouth? Going out. What direction is the sound wave going when it comes out of my mouth? It's going out as well. So that makes the wave a longitudinal wave because the displacement of the molecules is the same direction as the waves traveling. So sound waves are longitudinal waves. Light waves, which we can't do a simple explanation like this for, are transverse waves. But sound waves are longitudinal waves. Two different types of waves, fundamentally different types of waves. So now we can see a diagram of what was happening when we had the sound wave in this tube. Now this tube is open on both ends. Open on both ends, we call that an open tube. And you have a sound wave going in there. And for now, let's just focus on the sound traveling through the pipe. The point here is not to talk about why it was louder or softer, but to just look at the sound wave. What direction are the actual molecules traveling in that tube? Okay, in general, yes, they are moving everywhere, but the wave part of the motion is horizontal. I actually used to go to, we only have 3 minutes, so I'm not going to here, a website that shows the motion of the molecules. So you have them moving up, down, and all around, but the general motion is back and forth. So you have places where you have the molecules are closer together. We call those compressions. Places where they are rarer, we call those rarefactions. So rarefactions is where you have the molecules farther apart. Compressions where they're closer together. Compressions, you have high pressure. Rarefactions, you have low pressure. And so this wave, those places where you have the rarefactions and the compressions, those are just going to be moving constantly in one direction, the direction the wave is traveling. So if the wave is going from the tuning fork, then your wave speed is like that. And so in time, you would just see these compressions move. Can you determine from this picture what the wavelength is? Obviously, you can't give a number to it, but how would you identify what the wavelength is? Yeah, the wavelength is the distance to repeat. And so it repeats in that distance. So that's the wavelength. Just so you can understand how a radio speaker works, or any loudspeaker, a loudspeaker is basically like this pie pan without the mold. It's like this, and you have something. Wow, there's even more mold on the bottom side of the water. That's something special. It goes in and out. You have something that's driving it in and out. It's magnets that pushes it in and out. And since it's going in and out, it's pushing air in and out, making our sound waves, our disturbances passing through the air. Okay, we are at a good stopping point here. So I will see you in class on Wednesday. And remember, Wednesday will be a review day. You will not have to do a potential test question on Wednesday because it's a review day. But then Friday, we will be starting in with the next chapter, with chemistry.